Okay, this is section 4.1, exponential functions. Chapter 4 is probably my favorite chapter in the entire course. I really enjoyed this material. We have a lot of little information to pick up. We have some calculator work we have to learn how to do. We're just going to start off with an exponential function f with a base b is defined by f of x is equal to b to the x, or y is equal to b to the x, where b is a positive constant other than 1, and x is any real number. Now, what makes this different from the polynomials we were dealing with in the last chapter is that in the previous chapter, we had things like x squared, where our variable was the base and our number was the exponent. And now we're going to be dealing with things like this, 2 to the x. It's a very different animal, okay? There are some things we have to learn how to do on our calculators, just in case. And I have several with me. So let's start off with this one, okay? If I want to calculate 5 to the square root 3 power, you hit 5, and then on this button, this calculator, this is your exponent button. So you hit that, and then you can see that it comes up there. And then you need to get your square root, which is above this one. So second, and then that. And we have that, and now enter the 3 and hit enter, and you get that big ugly decimal. You're almost always going to get big ugly decimals. Now we're supposed to approximate, and we're supposed to round to 3 places. So this would be 16.24, that's a 4, so that's going to stay a 2. So this is approximately 16.242. Okay. I'm going to do the same thing with this calculator. It's pretty much the same. The buttons are pretty much in the same position. See right here, this was our exponent button on this one. This is our exponent button on this one. Okay, so I would enter the same thing. Everything else is basically the same. 5 raised to the, you have to hit second and then that square root, and then 3 and enter, and you'll get the same decimal. On the TI-84, your exponent button is right here. All right, so we have that approximation. Now let's do 3 to the 2.4 power. Okay. So 3 exponent 2.4, enter. We're supposed to round to 3 decimal places. So that's going to be 966. That should jump up to, that means that one goes up to a 7. So this is approximately 13.967. You really want to make sure you round correctly. The computer's going to count it wrong if you don't. And I know that you know how to do it, so slow yourself down and make sure you rounded correctly. These little squiggly equal signs, that means it's approximately equal to. It's an indication that there has been some sort of rounding and that it is not an exact answer. Okay, so what we're going to talk about now is a general idea of what the graphs of these things look like. There are 2 major cases. There is the case where the number is larger than 1, and there is the case where the number is smaller than 1. We're going to do a graph of both, okay? First thing I'm going to do here, I have 2 to the x power, and I'm going to plug in these values and see what I get, okay? So if I do 2 to the negative 3, we should know that that's the same thing as 1 over 2 cubed, which is 1/8. Okay, so 1/8. If I do 2 to the negative 2, that's 1 over 2 squared, which is 1/4. To the negative 1 power, that's going to be 1/2. Anything to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. You should see some sort of parallel here. You can see that those are in the denominators. Okay, so I'm going to estimate these points. Okay, so at negative 3, I'm at approximately 1/8. At negative 2, I'm at 1/4, so slightly above. This is hard to do. Negative 1 is I'm at 1/2, so just slightly above. And then at 0, I'm at 1. So far it's growing pretty slowly. But then once I get to 1, it goes to 2. And then 2, it goes to 4. And 3, it goes up to 8. And then if I went to 4, it would be up at 16. So what happens here is this graph starts off really small and it's growing really slowly until all of a sudden it shoots up. Okay, this is an example of exponential growth. And this was actually talked about a whole lot at the beginning of the COVID-19 pandemic. At the very beginning, the scientists were saying that the number of cases was growing exponentially, which was true, but to the mass public, it looked like it wasn't doing anything at all. It wasn't growing very quickly at all. And we are used to hearing it's growing exponentially, meaning it's growing very fast. But it's deceptive because it starts off growing very, very slowly. So back in February and March and April, we were in this part of the coronavirus, and then all of a sudden it shot up in the air. Okay? So this is exponential growth. It happens when this number is larger than 1. It could even be 1.1 or 1.0001. As long as it's larger than 1, it's going to behave in that basic way. Okay, so this is its counterpart. Instead of 2 to the x, I have 1/2 to the x. This is not going to be exponential growth. So if I plug in -3, I have 1/2 to the -3 power. Using our power rules, this is the same thing as 2 over 1 to the +3, which is 8. Okay, analogous, let's jump down here. If I do 1/2 to the 3rd power, that's 1 over 8. Okay, if I do -2, that's 1/2 to the -2, which is the same as 2 squared, which is 4. But if I did 1/2 squared, I get 1/4. You should see that you're getting the same values as you did on the previous page. It's just in the opposite order. Where -3 went to 1/8 and +3 went to 8, it is now exactly the opposite, which means the others here are easy to plug in too. 1/2 to the -1 power would be 2, 1/2 to the 1st power is 1/2, and anything to the 0 power is 1. So this line of the chart is the same. So let's try plotting these points. At -3, I am at 8. At -2, I am at 4. -1 at 2, 0, 1, 1/2, 1/4, 1/8, and then it would go to 1/16 and even smaller. Okay, so this graph goes down really quickly and then sort of levels off and slows down quite a bit. Okay. This is an example of exponential decay. Exponential decay in the real world, when you hear about the half-life of a radioactive element, how long does it take to get for a radioactive element to reduce to half of its original size? Or how long does it take your body to expel a certain drug? These are all in this sort of realm. And it has everything to do with this number being smaller than 1. It could be like 0.99999 and it's still going to go down. Okay? So let's talk a little bit about some of the characteristics of this thing in general. Okay, so this is not specific to whether this B value is less than 1 or greater than 1. The domain is all real numbers. We are allowed to plug in any exponent on that. But the range is from 0 to infinity, and we never get to 0. There is nothing I could plug into this x and do the arithmetic and end up with a 0. There's also no way I can end up with a negative answer. That's why on both graphs, we get really close to the x-axis, but we don't cross it. Okay? All of them must pass through the point 0, 1. And I said earlier that these are the same on the chart, And that's because it doesn't matter whether this is greater than 1 or less than 1. If you raise it to the 0 power, it is 1. So you have right here. Okay? If b is greater than 1, then the graph is increasing, which was example we saw right here. And also, the larger the b value, it increases faster. So if this is 2 to the x, this would be 3 to the x. This would be 4 to the x, and so on. It just grows that much more quickly. And it's exactly the opposite for the b value less than 1. If the b value is less than 1, then it's decreasing, and then the smaller it gets, it decreases faster. So if I have 0.999, it's going to decrease, but not that quickly. But if it's 0.0001, it's going to decrease very quickly. Okay? The function is 1 to 1, and it has an inverse that is a function. We're going to be dealing a lot with these inverses. We're going to be talking about exponentials and their inverses throughout this entire chapter. And then basically, I said this earlier, the x-axis is a horizontal asymptote. You're going to get really close to that x-axis, but you're never going to cross it.